In this session, we are going to explain the MapReduce component of Hadoop. But before we start understanding MapReduce, we need to have the basic understanding of big data and an overview of Hadoop, and also an in-depth understanding of how the Hadoop distributed file system works. MapReduce is the heart of Hadoop. It is the programming paradigm that allows for massive scalability across hundreds or thousands of servers in a Hadoop cluster. The MapReduce concept is fairly simple to understand for those who are familiar with clustered scale-out data processing solutions. The term MapReduce refers to two separate and distinct tasks that Hadoop programs perform. The first is the map job, which takes a set of data and converts it into another set of data, where individual elements are broken down into key-value pairs. The reduce job takes the output from a map as input and combines those data tuples into a smaller set of tuples. As the sequence of the name MapReduce implies, the reduce job is always performed after the map job. Instead of moving large amounts of data around, it is far more efficient, if possible, to move the code to the data. The complex task of this is one of the principles on which MapReduce is based. MapReduce also allows programs to scale transparently. The complex task of managing storage in such a processing environment is typically handled by a distributed file system that sits underneath MapReduce. Now look at how the computation of MapReduce works. Conceptually, this can be explained in a real-life example of summarizing an entire book. We have a book which has a lot of chapters in it, and we need to summarize it as quickly as possible. To achieve this using the MapReduce paradigm, we will first get the summary of each and every chapter individually. And then, once we get all the summaries of the individual chapters, we will aggregate all those summaries and consolidate it into one big summary of the entire book. This is how the MapReduce paradigm works. A bigger job is a complete program that executes the mapper and the reducer across a dataset. Execution of mapper or reducer is done on a portion of the data which is known as a task, and a particular instance of an attempt to finish a task on a machine is called the task attempt. The MapReduce architecture follows the master-slave architecture. The mapper and the reducer tasks run on top of the data nodes. Processing moves at the location of data instead of moving the data to the location of processing. For MapReduce, the job tracker keeps track of all the task trackers. If some data loss happens, the job tracker will immediately contact the data node and get the replication details and allocate the task tracker. Now let's look at the data flow when a MapReduce program is executed. The input data is broken down into key-value pairs and fed to the mapper. The job tracker assigns multiple mapper tasks to process on the smaller chunks of data. Once the mapper completes its execution, the output is grouped and sorted together by the keys of the mapper output, and similar keys are sent to the reducer. The reducer then aggregates over those keys and their corresponding values and writes the final output data. The shuffle and sort phases are intermediate steps between the mapper and the reducer, and they are performed by the MapReduce framework itself. If required, they can also be customized. There is another phase in the MapReduce framework which is used to reduce data transfer between mapper nodes and the reducer nodes. That phase is known as the combiner phase. It runs on the map output on the mapper node, and the output of the combiner forms the input to the reducer. It can be executed for commutative and associative reducer functions, although it is an optimization function, so it is not guaranteed that the combiner will be executed every time by the MapReduce framework. Another important phase in the MapReduce framework is the partitioner. A partitioner works like a condition in processing an input dataset. The partition phase takes place after the map phase and before the reduce phase. The number of partitioners is equal to the number of reducers. That means that a partitioner will divide the data according to the number of reducers. A partitioner partitions the key value pairs of intermediate map outputs. It partitions the data using a user-defined condition which works like a hash function. The partitioner task accepts the key value pairs from the map task as its input and divides the data into segments according to the given partition criteria. The partition logic is to read a field from the key value pair of the input, and then if the condition applied is satisfied, then the whole data of the key value pairs are segmented into a collection of key value pairs, and then that whole collection is sent to the reducer. The reduce tasks now work individually on each of these collections. The default partitioner is a hash partitioner, but we can also customize the partitioning phase because the partitioner has direct impact on the global performance of the job, and any poorly designed partition function will not distribute the task over the reducers. Sometimes it becomes necessary to control the key value pairs partitioning over the reducers. So the MapReduce framework also provisions writing customized partitioners. To provide mechanisms for serialization and deserialization of data, Hadoop provides multiple classes for data types. Hadoop data types used in MapReduce for key or value fields must satisfy the constraints that any data type used for a value field in the mapper or the reducer must implement writable interface, and any data type used for the key field in the mapper or the reducer must implement the writable comparable interface along with the writable interface to compare the keys of this type with each other for sorting purposes. The classes wrap the Java primitive types and implement the writable comparable and writable interfaces. All the writable wrapper classes have the get and set method for retrieving and storing the wrapped values. Hadoop provides these classes to wrap the Java primitive types, and the various primitive writable wrappers are boolean writables, byte writables, int, float writable, long writable, and int writable, and double writable. The input formats define how to read data from a file into the mapper instances. Hadoop comes with several implementations of input format. Some work with text files and describe different ways in which the text files can be interpreted. Others, like sequence file input formats, are purpose-built for reading particular binary files. We can also define our own input format implementations to format the output of our programs however we want. Hadoop also provides output formats that corresponds to each input format. Output formats describe the output specification for a MapReduce job. Based on the output specification, MapReduce job checks that the output directory doesn't already exist, and the output format provides the record writer implementation to be used to write out the output files of the job. Similar to the input formats, the output formats can also be customized based on how we want to read our files in our MapReduce program. With big data, MapReduce is always the first term that comes into mind, but it's not the only way to handle large amounts of data. There are database systems especially built to deal with huge amounts of data, and they are called massively parallel processing or MPP databases. These MPP database systems have been around for a longer time than MapReduce and its most popular integration, Hadoop, and are based on shared nothing architecture. The data is partitioned across several nodes of hardware, and queries are processed via network interconnected on a central server. They often use commodity hardware that is as inexpensive as hardware for MapReduce. For working with data, they have the advantage to make use of SQL as their interface, the language used by most data scientists and other analytical professionals so far. MapReduce provides a Java interface to analyze the data, which comes with more time to implement than just write an SQL statement. Since both systems handle data, there will be a lot gained when both are combined. Here we will compare MPP with the MapReduce framework. Hadoop has some projects that provides a SQL similar query language like Hive, but query optimization is better in MPP, whereas in Hadoop it's poor to none. MapReduce provides a Java interface to analyze the data, which comes with more time to implement than writing and debugging SQL queries. So the debugging level of MPP is easier compared to Hadoop. Also, the administrator skill level for MPP is relatively lower than that of Hadoop. MPP is not the best choice for high concurrency and 100 plus server clusters, whereas Hadoop can handle high concurrency and it can scale up to more than 5000 servers. So to summarize, we saw how MapReduce works and how job management is done in the MapReduce framework. We saw the various phases of the MapReduce framework, and we also compared MPP with MapReduce to provide an idea of the scenarios MapReduce works best. The next sessions will concentrate on hands-on execution of a MapReduce program.